Hello students, in this lecture we are going to continue looking at virtual memory. A quick recap of how it works. From the processor we get virtual address. We divide that into two fields, page offset and virtual page number. Page offset depends on the page size. We have page table register which has the starting address of the page table. It will point us to the location of the page table. Page table has entries which are called page table entries. One entry would be typically having physical page number along with some status bits like recency bit or valid bit, dirty bit, etc. To the page table to the page table register value, we add the virtual page number and we get the index of this page table. It selects one entry in the page table. From there we get the physical page number to which we append the page offset, and together we have the physical address to the DRAM. Now with this address we are going to access the main memory again. Now what happens if the virtual address space is huge? Let's look at some implementation details. How long should be the page table? Typically it should be as long as the width of the virtual page number field. Now for RISC-V, if we consider a 48-bit virtual address and 12 bits of page offset, it means that the virtual page number would be 36-bit long. It means that my page table should have 2 power 36 entries. Another problem is how much space does this page table take? For that we need to know what is the size requirement of one page table entry. As we have just seen, each page table entry has some status bits and physical page number. Let's say the physical page number is something like 20-bit long. Along with that we have, let's say, 4 bits of status. It means that 24 bits. So we have nearly 5 bytes of each, 4 bytes or rather 3 bytes for each page table entry. 3 to 4 bytes you can say, based on the physical page number. Now if we need 4 bytes for each page table entry and we have 2 power 36 entries, then the page table itself would require nearly 1 gigabyte of memory. This is for one program. Now as we know, there will be a page table for each of the program that we are running. Now if each program can typically take 1 gigabyte or so, this only for the page table, we need space to actually store the data of the program, store the instructions of the program, so on and so forth. So our main memory capacity will not be sufficient at all, because it will be just made up with the huge page tables. How do we handle this situation? There are multiple design choices to make a page table. So we are going to look at 5 different methods at an abstract. The first method is limit the page table size. Instead of going for, let's say, 2 power 36 entries, we are going to say that there will be only 1024 entries at any given moment, or to start with. Now if some particular program uses up all these 1024 entries and it needs one new entry, based on the demand, we are going to extend the page table. So instead of having 2 power 36 for all the programs, we are going to have dynamic page table sizes based on the program requirement. Second method is to use separate page tables for separate segments of the program. Now, as you are aware, the text segment and data segment remain same during the execution of the program, but the stack and heap are dynamic in nature and they vary in their size. So another method would be use separate page tables for each of these segments and expand them like our previous idea on demand. So we can have one separate page table for stack data, another for heap data, another for text, and another for the actual data. Third method is to opt for hashing, wherein we take the 36-bit virtual address and convert it into some smaller index using which we are going to index into the page table. The fourth technique is we have such huge page table. Let's divide the page table itself into multiple pages and bring in only part of those pages or few of those pages into the main memory on demand. The fifth one, quite popular, is multi-level page table. Here we are going to use a hierarchical decoding. It means, for example, we can do a 10-bit decoding, all the 10 bits at a time, or we can do few bits, let's say the MSB 2 bits at a time. Based on the output, we are going to decode few other bits, so on and so forth, as a tree. So multi-level page table works like a tree. This is what a RISC-V approach is. The base address of the first page table is stored in SPTBR, which is supervisor page table base register. From this, we are going to use few bits of the, so as shown in the figure, we are going to use this base address, and to which the virtual address 8 bits are used to index into the level 0 page table. The level 0 page table gives us the base address of the level 1 page table, to which we are going to add 8 or 9 more bits from the virtual address, which are 38 to 30. From here we are going to get the base address of the second page table, so on and so forth. So here one huge page table is divided into multiple smaller page tables, and eventually we are going to get the actual physical address. In RISC-V, each page table entry is almost 8 bytes long, and each of these page tables in level 0, level 1, level 2, level 3 are having 512 entries. The rationale behind that is each entry is 8 bytes. So to make sure that each page table itself fits in one page of 4 kilobyte, they have 512 entries. So we need 9 bits to index into level 0, 9 bits more to index into level 1, 9 bits more to index into level 2, so on and so forth. So this was the most practical way of implementing a huge page table. Now, if you remember, we did a small food for thought exercise wherein we were counting how many accesses would it take to get the data from the main memory. The first access would be to the page table, which is actually in the memory. From there, we are going to get the actual physical address, and we are going to use the physical address and then go to the location of the actual data we would need. So every memory access needs to talk to it twice. It takes twice the time now. If we say that memory access time is 80 cycles, now it would take 160 cycles for every time we are trying to access the memory. So this as you already guessed, is too penalizing. We are incurring too much of delay, which will eventually reflect as pipeline stalls. And this can happen for any of the instruction fetch or in the memory access stage for either load or restore. Again, we have our principle of locality to the rescue. Here the locality is interpreted like, if even though the program is divided into, let's say, 1024 pages, for example, at any given moment it's going to access only a subset of it, let's say 5 to 10. So if we are able to get these 5 to 10 pages translations faster, it would mean my overall program would run faster. So with this motivation, the question was, why don't we cache these few important pages translations in a separate place? And that is called translation look aside buffer, TLB. So TLB is like a cache for the page table itself. Just like we have the regular L1, L2, L3 caches for the main memory, and main memory is the cache for the secondary memory, here TLB is a cache for page table, and page table has only translations. So TLB has only the virtual memory to the physical memory, or virtual address to the physical address translations. It's a cache of those translations. Just like our L1 and L2 caches, TLB is an exclusive hardware, whereas page table was residing in the main memory itself. Typical page table entry would be having the virtual page number, physical page number, along with few other status bits. A TLB lookup, just like a cache lookup, can be a hit or a miss. Upon a hit, we access the main memory only once because we already have the physical address. But on a miss, now we need to access the page table, from where we are going to get the physical address and again access the main memory. So upon a TLB miss, we would incur twice the memory access latency. Oh, sorry for this. Now let's look at the TLB working a little more. Just like we tried to answer the working of caches, page table, basically the virtual memory, by answering 4 questions, let's look at those 4 questions here again. Where do I place an entry in the page table, and how do I find an entry in the page table? The TLB is a fully associative structure. It means that any virtual address to the physical address translation can sit anywhere in the TLB, and TLB accesses would be fast even though they are fully associative because they are typically small. Now what happens on a TLB miss? We already know. The request is forwarded to the page table. In the meantime, the page table needs to find a replacement candidate. Here it is any translation which was not used in the recent time. So typically LRU policy is used. What happens on a write? Because these are only translations, the TLBs don't actually have writes. What the dirty bit status in a translation indicates, it means that the data in the page for which this translation is there has been changed by the processor. It's not that the translation itself has been changed. So don't get confused. In order to reduce the number of transactions between the TLB and the page table, which is in the main memory, typically we use write back policy. Now, who manages the TLB? The page table was managed by both the hardware and software, specifically the OS. The TLB is managed by an exclusive hardware which is called Memory Management Unit, MMU. Typical values of a TLB would be the size is somewhere between 16 to 512 entries. That is the reason we said the TLBs are usually small. The block size, it means one entry in the TLB has 1 to 2 page table entries. Then the hit time is less than 1 clock cycle. We'll see the impact of this a little later. The miss penalty is hundreds of clock cycles because we are going to access the main memory. Usually because we are caching the translations, each translation corresponds to 4 kilobytes. The miss rates of TLBs are quite small, anything less than 1% typically. In modern process, we don't have one TLB, but just like we have an instruction cache and a data cache, we have a dedicated TLB for instruction translations and a dedicated TLB for data addresses translations, so that both of them can work in parallel. Also, we have multiple levels of TLB, just like we have multiple levels of caches. Typically, 2 levels of TLB is quite common in all the modern day processors. Overall, if we look at the virtual memory and TLB working, the processor would generate virtual addresses which will go through the MMU from where we get the physical address. We use the physical address to look up to the cache and the main memory and eventually the disk storage. Now, the virtual memory we were discussing so far was handling only the main memory. We did not look at the cache. But let's introduce the cache part now. Will the cache work with virtual addresses or physical addresses? Before that, the memory management unit is a specialized hardware specifically for these address translations. The TLBs themselves reside in the MMU. Also, MMU manages the the page table lookups. It means that the MMU has the access to the page table register, the base address of the page table, to which it will add the virtual address and get the address to using which it needs to access the main memory, so on and so forth. Then if it finds that some particular entry is not residing in the page table in the memory, it signals the OS saying that there is a page fault. The OS will take over the control using an interrupt service routine, and it will generate a request to the disk storage or the secondary storage from where it would need to bring that page to the main memory using the DMA transfer. Now, the question I asked just before was, are we using the physical address or virtual address in the caches? That will decide the answer to this question. How are the TLB and cache placed? Are they placed one after another or side by side? If we have the TLB in between the processor and the cache, like in this figure, the MMU has TLB, the virtual address would go to the TLB and TLB will give us the physical address. Using the physical address, we are going to look up to the cache. It means that every access to the cache needs to go through the TLB, and the TLB access time, like we saw earlier, is anywhere between a half cycle to 1 cycle is added to the cache access latency. It means every instruction fetch now can typically take 2 cycles. Every load and store can take 2 cycles. What it translates to is every time we are trying to access the instruction cache, we have 1 cycle stall. The performance drops by 50% right away. Now, the designers wanted to do something better with it. How can we avoid the TLB access latency when we are looking up to the caches? For that, we have 4 possible design choices. The first one is virtually indexed, virtually tagged cache. What it means is the caches work with virtual addresses. It means that the tags which are stored in the tag array are the virtual tags. The TLB and cache can now work in parallel because we don't need the physical address at all. So the TLB cache, L1 cache here, both take the virtual address generated by the processor and work in parallel. So the access latency of TLB is no longer in our critical path. So we are able to complete an access to the cache if it takes one cycle within that processor cycle. So there are no extra stalls. All looks good. But the catch here is aliasing. What does aliasing mean? Multiple programs, because each we are at the processor we are only dealing with the virtual addresses, they can have the same virtual addresses. For example, location 1000 for program 1 and location 1000 for program 2 are actually different, but if the cache is storing both of them in the same location because it's using this virtual address 1000, it means that we end up giving the data of one program to another, or we don't know that the location 1000 which we stored in the cache belongs to program 1 or program 2. This problem is called aliasing. It will sabotage our instruction execution because the final answer can be random and it's like garbage out. We can't make any sense out of it. So virtually indexed, virtually tagged caches are not the design choice. The second option is physically indexed, physically tagged. It means that the caches are working with the physical addresses, just like we saw in the previous slide. So here the TLB axis and the cache axis are in series. The virtual address is first taken up by the TLB. It would generate the physical address, which is again used up by the cache. So every time we are trying to access the cache, we need 2 cycles minimum. So we have 50% drop in the performance right away. So it's not a design option. Here comes the 6th cache optimization, which I skipped in the lecture where we were discussing the other optimizations. The designers observed that the cache access happens in steps. If you remember, the very first thing we do is we extract the index bits from using which we are going to select one particular row which has both the tag and data. We are going to read out the tag and the data to the end of the tag array and data array. At that point, we use the requested tag for equality check. It means whether the tag we are storing in the cache is same as the requested tag. If it is same, then we said that it would be a tag hit. Sorry, cache hit. Otherwise, it's a cache miss. So we would need index bits first. Tag bits can come a little later. So using this detailed working of the cache, the third solution is proposed, which is virtually indexed, physically tagged cache. Here, the TLB and cache can work in parallel. How? The cache stores physical tags here. So the TLB will consume the virtual address. In parallel, the cache takes only the index bits from this virtual address, uses that for its row decoder. It will select one particular set, all the tags and data will be read out. In the meantime, the TLB will supply us with the physical tag. This physical tag will be compared with the tags we read from the tag array of the cache. So if we are able to manage the TLB access in 0.5 cycles, if the cache is taking 1 cycle, it means in the second half of this cycle, the physical tag which we need is ready. So this is the most popular and widely used implementation of the TLB and cache, wherein we are using the virtual index bits to select a set and physical tags to eventually find out whether it is a hit or a miss. Because we are using the physical tags, there is no aliasing here. Program 1's tags and program 2's tags are different because they are physically stored in different locations in the main memory. The last option, just for completion, is physically indexed virtually tagged. It means that we are using physical index bits to select a row and so on and so forth. It means that we are already accessing the TLB in series. So this is similar to the method 2 above. So virtually indexed physically tagged cache is the sixth optimization for L1 caches. For L2, L3, L4 and beyond, anyways the TLB access would have happened by then, so we have the physical address. So the sixth optimization pertains to the L1 cache, specifically reducing its hit time. This way we are able to reduce the impact of TLB lookups on the overall AMAT. With that, we complete the virtual memory concept. I would like all of you to go through section 5.7 in Computer Organization and Design book and Appendix C4 from Computer Architecture, a Quantitative Approach book by Patterson and Hennessy. So this Appendix C4 is more or less a high level view, and section 5.7 goes through a little more in detail. So you need not completely read through 5.7. You can skip the segmentation part. Also, you would need to read only till page number 839. So go through them. If you have any doubts, post it on the classroom. We can discuss further. With that, I'll conclude this lecture. Thank you.